Up until now, we've only considered what happens if you have a capacitor that has in between its plates a vacuum. Um, and the question is, what if we put something else in between the plates of the capacitor? And that something else is typically called a dielectric. In fact, if you really, technically, I guess we could call vacuum a dielectric. But anything that we put into a capacitor is called a dielectric. Most of this little explanation is going to be conceptual. The math turns out to be stunningly easy, but the concepts are really worth getting your mind wrapped around because they're significant and they help us understand how to use dielectrics. So what happens if we put something between the plates? Well, if we put something in between the plates, it better be an insulator. Otherwise, there's kind of no point, right? If the material in between the plates is a conductor, it's going to bleed off all the charge from one side to the other. So another thing that is true is that pretty much all insulating materials, so meaning materials that charge doesn't move around freely from one place to another, and are to some degree polarizable. And that turns out to be the crucial thing for the purposes of a capacitor. So let's suppose we put some material other than a vacuum in between the plates, and we're going to look way up close at this material, and we're going to say, what happens if this material is in there, in between the plates with charge on both sides and an electric field running through it? So let's look up super close at a chunk of material. So materials are made of molecules, and molecules are made up of atoms, and atoms are made up of particles that are charged, positive and negative. And those positive and negative charges are not always in exactly the same place at exactly the same time. And in fact, where they are can sort of be smudged by the presence of a field. Or alternatively speaking, there's some molecules that naturally have one end of the molecule a little bit positive and a little bit the other end of the molecule a little bit negative. Water is a perfect example, otherwise microwave ovens wouldn't work. But in the presence of an electric field, pretty much all molecules will smush themselves into separating to a little bit of a positive end and a little bit of a negative end. And so the question is, what happens if we take one of these materials and we expose it to an electric field? Well, what happens is the molecules polarize and then they align with the field, which is to say, if the molecule can't move around because this material is an insulator, but it can turn, then the positive ends will get pushed downstream in the field and the negative ends will get pulled upstream in the field, and our molecules align. Notice that our material is still net neutral. If we look at a chunk of it in the middle, we'll still find as much positive charge as negative charge. But look very carefully at the edges. The top and bottom edges of our material are not net neutral. In fact, what we've done is we've built up a very small amount of negative charge on one surface and a positive charge on the other surface, right? Still, we're talking about an insulator. The charges don't move around, but by aligning the molecules, we can build up a little bit of layer of charge on one end and on the other end. Well, this charge is going to also cause field going from the positive to the negative. And notice that that field opposes the external field. That's going to cancel out some of the external field. This has the net result that a dielectric in an external field actually weakens that field inside the dielectric. Or another way of thinking about it, a dielectric only permits some of that electric field to penetrate. So let's recap that really quickly. If we have a material and we impose an external electric field, only some of the electric field is going to get inside. The amount is going to depend on the material, right? Some materials, they polarize more easily. You can get their positives and negatives to separate to a greater degree, or they rotate more easily. But depending on the material, more or less of the field will penetrate. But I think we can pretty much guarantee that some of the field won't penetrate. And what this means is that the voltage difference, the change in potential, is going to change. Why is it going to change? Well, how do we find the change in potential? We find it, in this case, if the E field is uniform, it's really simple. We don't have to do an integral. We take the E field and we multiply it by the distance And so in this case, if the E field has gotten weaker, then the difference in potential from one side of the dielectric to the other has gotten less because the E field has gotten less. So what does this have to do with capacitors? All right, let's charge a capacitor with a dielectric inside. Okay, now this is just a dramatization. I'm going to talk through this in little tiny steps as if little tiny steps happened in the process. But in fact, equilibrium happens really differently. Like the systems equilibrate electrically in a much smoother way than this. But conceptually speaking, this is what's going on. So we've got a capacitor here, a really simple parallel plate capacitor, and it's connected up to a power supply. And we're going to turn on this power supply to charge the capacitor. But first, let's just ask momentarily, what is a power supply? Well, a power supply is just a device that says, hey, I'm going to move charge until I've gotten to some particular voltage that I've been asked to arrive at. Right? It's like I'm going to pump charge until the potential difference between the ends of the power supply is the potential difference that is being asked for. So when we turn on our power supply, it pumps charge on here. Obviously, it's pumping negatives onto the bottom and off of the top, but it's the same as if it were pumping positives onto the top and negatives onto the bottom. Anyway, we established that charge. We put a Q on one plate that establishes the potential difference between the two things because of the electric field in between. Remember, why is there difference in potential? There's a difference in potential because of the presence of the electric field between the plates. So what happens if we put in the dielectric? Oh, before we've got an electric field, we can figure out what the capacitance of this capacitor is, right? We know the amount of charge that's put on there. We know the potential difference. We find the capacitance is the charge divided by the potential difference. If we put in a dielectric, what did we say? We said that the dielectric has the effect of weakening the field. It makes some of this field go away. Now, if that happens, remember, the power supply said, hey, I got to move charge until I reach the potential, until I reach the difference in voltage that I've been set to. And so if we've dropped in this dielectric that's dropped the field, we've all of a sudden dropped the potential difference. How is the power supply going to respond? It's going to respond by continuing to move charge until that potential difference is established. So the power supply adds more charge. And when it adds more charge, that creates more electric field. And essentially, it's going to keep on adding charge until we get the electric field that will be associated with the potential difference that we've set the power supply to. But notice what's happened. In doing that, we've had to add more charge than we used to in order to charge this capacitor. And the capacitance of this capacitor is defined in terms of that charge. If we've got more charge to get the same potential difference, well, that means that the capacitance has changed. So let's put this all together. Dielectrics are polarizable insulators that have the effect of weakening E field. And so that means in a capacitor, they lower the potential difference, or alternatively, they raise the charge necessary to get that original potential difference. And this has the effect of raising the capacitance. That's the concept. Dielectrics raise capacitance. And in fact, that's it for the conceptual part. And the math is really, really simple. So if you get that, dielectrics are polarizable insulators that weaken field, which has the effect of lowering potential difference and raising the necessary charge to get that potential difference and raising the capacitance, then you can do the math. And the math is really simple. Ready? All dielectrics can be described by a dielectric constant kappa. I know it looks like a K. Actually, it's a Greek kappa. And if you can handwrite a kappa so it looks different than a K, well, good for you, because I can't. All materials have dielectric constants, and you can go into the lab and measure them, but they've already been measured by thousands of labs before us that make up tables and tell us what are the dielectric constants of these various materials. A vacuum, by definition, has dielectric constant 0. Air has a dielectric constant dielectric constant of 1. Air has a dielectric constant very, very slightly higher than 1, and then pretty much everything else, like all serious materials that you could put inside of a dielectric, inside of a capacitor, have dielectric constants significantly greater than 1. So what does that mean? How does that play into our concept? What does the dielectric constant mean? Well, the dielectric constant is going to describe the degree to which all of those other effects happen, and it's going to describe them in really simple linear terms. So we said that a dielectric constant weakens the field. How much does it weaken the field? It weakens the field by a factor of kappa. The electric field inside of a dielectric is the same as the electric field that would have been there without the dielectric, divided by the dielectric constant kappa. So because of that, we know that the difference in potential, if we have a uniform field, is linearly related to the electric field. So the difference in potential is the difference in potential sub zero, the original one, the one that we would have had without a dielectric, divided by kappa. And this means that the capacitance of a capacitor that's been filled with a dielectric is greater by some factor kappa. So kappa times C naught, which is the capacitance that we would have without the dielectric present.